Hello guys, welcome back. Today we are going to understand the today Leetcode questions. So let's go and understand this one. So today question we have given is 1557 minimum number of vertices to reach all nodes, right? So that we are going to do today. Okay, so to understand that, first we have to go through the statement, right? What a statement is saying that. So in the statement it is saying that we have given a directed acyclic graph with n vertices, right? And it is numbered from 0 to n minus 1. So we have given a cyclic graph, right? We have given a cyclic graph, means it is we don't have cycle. It look like something like this, but it is not like cycle. Okay, as you can see. So if we will make the cycle, there is no any cycle, means it is not like this. There is no cycle. It is not like this. It is not like this, right? So this is not cyclic. Any of these will be there, so it will become cyclic, right? So this is not cyclic. Okay, understand? Now coming back to the statement, now it is saying that we have 0 to n minus 1, 0 to n minus 1. So if it is saying that vertices we have given 0 to n minus 1, definitely it means it is not a cyclic. It is a acyclic, right? Always remember that. Okay, now coming back to the statement, it is saying that where s of I is equal to from the index to index. So it represent if this is a index and this is the vertices. Let's suppose this is the edge we have. So if this is one vertices and this is another vertices, so this vertices is from I and this vertices from 2j, right? Like this, you can say. So this is your from and this is your 2. Okay, like this. So this is your edge. It is saying now it represent a directed edge from node from I to node 2i. Now we have to find the smallest set of vertices from which all the nodes in the graph are reachable. So it's a guarantee that a unique solution exists. It is a guarantee, means definitely there will be a unique solution. So we have to find the smallest set of vertices from which all the nodes in the graph are reachable. Okay, so that we will see in this you can say program, right? So let's understand. It is also saying that, notice that you return vertices in any order. You can return any order. Okay, so let's consider this example first. So in this example, let me go back. Yeah, now understand. So it is saying that let's consider this example. So in the example, as you can see, we have given these sets of vertices 1, 0, 2, 4, 5 and 3, like this we have given. So these are the edges we have given. So n is a number of you can say nodes we have given, vertices we have, 6 vertices we have given. So if you'll count from 0 to it is coming to 5. So all are able 0, 1, 2, 3, 4, 5, right? We have, right? So 0 to n minus 1 we have, 0 to n means 0 to 5, 0 to 5 nodes we have here. So each node is connected with other, right? And edges we have given like 0 to 1 means the direction is from 0 to 1, then 0 to, and then 2, 5, then 3, 4, as the example is saying the statement. So we have the direction, means 0 to 1 means it will go to 0 to 1, right? It is 0 to 2 means it will go to 0 to 2, like this. This is called directed acyclic graph, right? So as you can see, there is a direction from here to here. It is saying in the statement 0 to 1, 0 to 2, right? Means we have the given directions, right? Similarly, we have given 2 to 5, right? As you can see, then we have given what? 4 to 2, right? That we have given, and 3 to 4 we have also given. So these all are in the direction, right? We have given. Now it is saying that we have to find the smallest set of vertices from which all the nodes in the graph are reachable. So if you'll consider for which node we can traverse all each one, right? So as you can see here, we can from 0 we can go to 1, from 0 we can go 2, from 2 we can go to what 5, right? We can go, right, like this. Another what we have 3, so from 3 we can go to 4, from 4 we go to 3, and from 4 to 2, and 2 to 5 we can go, right? So it's not possible to reach all the nodes from the single vertex, right? From any, either you will see either 0 or either 3, right? But from 0, if you consider here 0, so we are going almost 0, we are going to 1, from 0 we are going to 0 to 1, 0 to 2, 0 to 5, right? We are going, right, like this. So we can go like this, right? So we can, and from 3 we can reach to 4, 2 and 5, right? So we can say that in both the common is 0 and 3 is the node, right? Smallest vertices we have. So these vertices can reach almost all the node, as you can see. So these are the set, we can say, and with this respect we can say that this will be our answer, the smallest set of vertices. So these are 2 vertices as the smallest set, we can say, and we have to return in any order, either 3 or 0 or 0 or 3, any of the order you can mention, right, as it is saying here, right? You can return that. So how we can find this type of solution, right? So to understand that, always remember that you have to focus on InDegree solution, right? So you have to check the InDegree. InDegree means you have to take care of incoming and outgoing edges, right? So where we have to find if there is n vertices that is connected with e edges, right? If there is n vertices and total edges are e, right? So we have to check if n vertices connected with the e edges, right, e directed edges, you can say, then there is no cycle, right? And we need to return the minimum set of vertices that are required so that all the vertices are reachable from these vertices, right? So first of all, let's find out the vertices that we can say we are sure won't be the final set, right? So let's consider some example, okay, and then we will go through to implement this one, okay? So in this example already we have seen we are going to this one is 0 to 1, right? So what I'll do, let me go back. Yeah, so let me come to erase this one. I'll erase this one so you will understand. Give me 1 second. Yeah, coming back to here, right? So what I have to do, we have from 0 to, if you'll see 1, right, means it is going to 0 to 1. Now it is, so InDegree, if you just consider for anything, means from 0 to 2, 0 to 1 we are going with 1 count. Another, if 0 is from 0 we are going to 2, means there is 2 count, just for understanding. Then we have to see another thing, means from 2 how many we are going, right? So from 2 we are going to 5, means from 2 we are going 1 time, right? And if you'll see another elements, right, means 5 we are not going anywhere, that is 0 it is going, right? Similarly, if you'll consider from 3 to 4, we have 3 here and 1, so 5 here we will put 0. And for 4 to going to 2, so we have InDegree for this element, right? So you can consider 4 and there is 1 element, right? So as you can see for 0, right, now 0 we have what, 2 times we are going here, right? So this is 2. So obviously that we have here is maximum, what we have the maximum going value, right, from here to here, right? So as you can see we are having this value and this value, right? As well we have all these elements for InDegree, like this one, these elements also. So we have to check the direction, right? So just opposite, if you'll do for the InDegree, right, from 0 it is going out degree is what, for 0 InDegree is actually 0 because it is not coming from anywhere, right, but it is sending. Similarly for 3, if you check the InDegree, it is going to 0, right? So for the 0 1 we have this one, right? We can consider 0 and this is the element from where we can check the direction. So always check the direction. Let me I'll explain again, don't worry. So I'm trying to say here actually if we have the element, right, so from 0 we are going to what, 1 and 2 we are going, right? So for InDegree of 0 there is no element because from any element we, like from 5 we are not going anywhere, we are not going anywhere, right? But it have the incoming is already there, right? So from 0 what we are incoming is InDegree is what we have 0. Similarly for InDegree for 3 is 0, but rest of the element have or not have, right, you can say. But rest of the element we have some InDegree, 1 InDegree, 1 2 InDegree, 1 InDegree, 1 InDegree, and rest is we don't have, right? So we have to check these 2 elements, right? 0 and 3 will be our output, as you can see, okay? If you remember the InDegree thing, right, that you will understand. So let's go to the coding section and you will understand how to define the InDegree, right? So let's understand. We are here on the browser section. Let's understand the problem, right? So to understand this question, we have already understand how we have to find the InDegree and those things, right? So now we have to we will collect all the vertices that are incoming is or not, means we have to find the InDegree, right? So incoming edges we will see and we'll check the we have or not, right? So we'll take a, let's suppose a boolean type value, and this will take a array of will contain all the incoming edges, right? So let's suppose we have incoming edge exist, right? And that is nothing but our new boolean, like this. I'll take like this, okay? And this element will nothing but our number of nodes, right? We have given already n. Now what we will do, we will check, we will mark all the edges and we will say the edge is there or not, right? To do that, first of all, what we have to do, for we are passing these edges, right, from here. So from here, each time we will get a list of it is a list of list, right? So we will take one list inside one element. So to take the one element, we have to say that is one, for this is a edge, like this. As you can see, one edge we will get from all the edges like this. And to traverse that, what we have to do, we will mark this edge, right? So at edge 0 we will have one node, right? So we'll check the same function. This is the function, right? And here we'll store the element, and the element will store what? Integer type. To get the integer type, what we will from edge, we will call a get method, because this is a list. From the list we'll get what? There is 0 and 1, right? So we'll check each edges, right? From here the element is there or not, right? So if the element is there, we'll say mark it as a true, means there is a you can say edge is there, right? Now this is done. Now what we have to, we have list all the, we have list to assign the vertices has incoming edge or not. So from here we will have our incoming edges, means at 0 there is a sender. Let's suppose we are talking about from in our example it was sending from what? 1 to, we are going to from 0 to 1. Let's suppose we are sending from what? 0 to 1 was a direction, right? So in this case, at 0 we have some element, but at 1 we will find the incoming edge. So incoming edge is coming from what? 0. So we'll store from here, okay? You got it? Now coming back to how many required edges nodes are there, that we will find, right? To find that, this is, sorry, not incoming edges, but let me take this value, okay? So I'll take this value, let me remove this one, and we'll say this is our required nodes, right? So I'll take required nodes, and this is nothing but our new array list. I'll take like this, okay? Now you have all these nodes, and then we will mark our node. We'll start from our index 0, and for all the nodes we'll go like this, and we'll say plus plus. So we are actually traversing the nodes, and for we will store all the nodes that cannot have incoming edge, right? So we will check that one, right? So to check that, we will have our data, right? So is incoming, we'll find, right? Incoming edge exist or not. So we will pass here, and here we'll check the I each time, each node. If there is we don't have, right, it means we have to add onto these required nodes, right? Okay, and these required nodes are required vertices, you can say, nodes, you can say, right? That we will just do add, and each time we will add our nodes, right? And finally, once we are done, we will return our required nodes, all the vertices, a set of vertices, a small vertices, list of small vertices will return. Let me zoom this, zoom out. Okay. Okay, I haven't passed equal. Submit this one. So it's working, okay? So now understand, you can say, complexity. To understand the complexity, what we have to do, we are going with all the edges, right? And we have n vertices. So time complexity will become what? If we have n vertices, and edge we have E, right? Because see, we are going with all the edges, right? See here, we are going with all the edges, so we are traversing all the edges. So for all edges we have to say O of E, and for all nodes we are going with this loop, so we'll say O of n plus E, right? Similarly, if we'll talk about the time complexity, space complexity, so we are storing on this boolean things, right? This is auxiliary space, that is not worry, but we are storing this one, right? So we have n edges we have, right? And we are storing the elements, so we will say a number of nodes we are going to add. For each node we have to define the incoming edge, right? So for the incoming edge we have to define O of n number of vertices. For all the nodes we will define, right? We'll check the you can say in order we have to find the in order, right? We have to mark true or false, right? If incoming edge is there or not. If incoming edge is not there, it means we have to find those lists that we have don't have the incoming edge, means that is a outgoing edge coming from here, right? And that will come over all the nodes we are traversing like that, right? So that's why we have to say node will come what O of n, right? And guys, if you like this video and it really help you, please hit subscribe this channel, so you will help in growing this channel. Thank you guys, thank you for watching this video.